cardinality of st-dicut. So I think it's the same.
Right. I think it's important to say that each of them has cardinality k or more, rather than there exists an st-cut of cardinality k or more. I think that those two are different.
Okay. Okay.
So that is a small caveat that I was missing. I kept writing there exists rather than saying for all.
Yeah. Okay.
Um, so yeah, that's problematic. Okay, so all right. Good morning, everyone. So in the last lecture, there was I bungled up a bit in stating the local edge version of Menger's theorem. So here is the corrected version. So this is the corrected version. For any graph G with specified vertices S and T, there exists k pairwise edge disjoint st-paths if and only if each st-cut has cardinality k or more. Okay, and this you can verify quite easily is equivalent to the corollary that we stated, that the maximum number of pairwise edge disjoint st-paths is equal to the cardinality of the minimum st-cut. Okay. All right. So are there any questions regarding this? Okay, so if not, after this, we looked at a more optimization viewpoint where we looked at a minimization problem and a maximization problem. And basically, the Menger's theorem says that the optimal solutions have the same cardinality. So if you can find k st-paths, and if that is the maximum you can do, edge disjoint, pairwise edge disjoint st-paths, then you will also be able to find an st-cut of the same cardinality, k. And that will be the minimum st-cut, right? And then we moved on to directed graphs because for the rest of this module, we will be focusing on directed graphs because all of the results for undirected graphs in this module, they turn out to be special cases or simple applications of directed graph results. Okay. So in this sense, directed graphs, at least in this module, are going to be more general and they are going to imply the results for undirected graphs. Okay. And we discussed the maximization problem, which is to find pairwise arc-disjoint st-dipaths, right? And you want to find a maximum, you want to find a set of maximum cardinality. Okay. So in a dipath, you need to pay attention to the direction, right? So when you say st-dipath, you're going from S to T, and all edges have to be oriented towards T. They have to be directed away from S and towards T, right? And so in that sense, a TS dipath is different from an ST dipath, right? Whereas in a graph, ST path is the same as TS path, right? Okay, so that's the maximization problem. And now the question is, what is the corresponding minimization problem? Okay, are there any questions? Okay. All right, if not, then let's take an example. Okay, so I'm probably going to use this example for a bunch of things in this lecture. Okay. So let's talk about cuts in directed graphs. Okay. So, well, a cut is very similar, but except that now we have some asymmetry. You see, in a graph, so when I say graph, I always mean undirected graph. And if I want to say directed graph, I will write digraph or directed graph. Okay. So in a graph, notice that if you take a set of vertices, x, then the complement is x bar, then partial x is the set of all edges going from x to x bar, right? So this set of edges is called partial x. Let me ask you the following question. Is partial x equal to partial x bar?
The graph, yes.
Right, exactly. So yes. So in a graph, this is true. In a directed graph, one has to be more careful as to what one means by a cut, right? So there are two types of edges now. There are two types of arcs, those going from x to x bar and those going from x bar to x. Okay. So we will use different notation for these two cuts. Okay. So partial plus of x is going to be the set of arcs that have tail in x and head in x bar. Okay. And just to remind you, for an arc, this is the tail and this is the head. Okay. And to distinguish this from the other possibility, we are going to use the notation partial minus of x. This is a set of arcs that have that have head in x and tail in x bar. Okay. Good. So now let's ask a question. So for a digraph, is partial plus of x the same as partial plus of x bar? Achyut, are you there? Achyut Prakash, are you there?
Yes, sir.
Okay, so what do you think about this question?
I think yes, sir.
Yes? Okay, let's look at an example. So let's take this set to be our x. Okay? Are you with me?
Yes, sir.
Okay. So I'm going to call these vertices v1, v2, v3, and v4. And now I want you to tell me what is partial plus of x.
It would be V2T
v2t, okay?
and V1, V4,
v1, v4,
S, V3.
s to v3. Okay. And what is partial plus of x bar? So remember, x bar is the complement of x.
Yes, sir. So all edges that leave from X bar, right?
Okay.
That would be, I guess, null set, right, sir? There's no, oh, yeah, null set.
Null set.
It-
Are you sure?
So V3, V4T, those are the edges which leave from X bar, right, sir? X bar
Leave
to X.
from X bar and go into
To
X.
X. So, yeah, I'm not able to find. Oh, sorry. Yeah, there is one V3, V2.
V3, V2. Okay. So now let's go back to the question. In a digraph, is partial x equal to partial plus of x bar?
No, no.
No. Okay. Thanks. Okay. Good. But can anyone tell me, I want to write something like this. Partial plus of x is equal to partial something. What can I write?
Partial minus of x bar.
Partial minus of
Partial
x.
minus of x bar.
Exactly. Thank you. Thank you. So this is true in a digraph, right? Okay. Also, in the example I chose, I did not have to put S on one side and T on the other side. I could have chosen any cut. It doesn't matter. Okay. So such sets are called dicuts of the digraph. So any such set of arcs is called a dicut of the digraph D. Okay. Good. All right. So now okay, so let's do a quick recap. What happened in the case of undirected graphs? In the case of undirected graphs, we were trying to pack as many st pairwise edge disjoint st paths, right? And what we realized is that if we have a small st cut, then we cannot pack more st paths than the number of edges in this cut, right? This is in the drawing where we, if there is an st cut of cardinality 3, then the best you can do is to have at most 3 pairwise edge disjoint st paths, right? In the case of digraphs, we are going to try to pack arc disjoint, pairwise arc disjoint st-dipaths. So what is going to be the corresponding notion for cuts? Anyone? What do you think is going to be the corresponding notion for cuts? What is the corresponding minimization problem? In other words, what type of cut is a die cut? What type of die cut is a bottleneck for having pairwise arc disjoint st dipaths? What kind of a die cut prevents you from having too many pairwise arc disjoint st dipaths? Anyone? No guesses? Okay, well, I'm going to have to call names. Harshit, are you there? Okay,
Yes,
so
sir.
what do you think? What kind of dicut will prevent us from having lots of pairwise arc disjoint st-dipaths?
Not sure.
No? Anyone else? Ravi Kiran, are you there? Okay, what about this example? This is a very simple example. Let me give you. Yeah.
Can we say like partial of x where x belongs to x?
Sorry, can you repeat that?
Partial of x where s belongs to x and t belongs to x bar.
Okay. By partial, you mean partial plus or partial minus or the union?
Partial plus.
Partial plus. Okay, exactly. So in fact, that turns out to be right. See, remember what you're trying to do is, supposing you have a die cut. S is here and T is here. And you have, let's say, 3 arcs going like this. Well, if you have exactly 3 arcs going from x to x bar, right? So we are looking at partial plus of x, where s is an x and t is an x bar. If you have such a die cut with exactly 3 arcs, then that means that you will not be able to have more than 3 die paths from S to T, right? So you will not be able to have more than 3 ST die paths in this directed graph, because each ST die path will have to use at least one of these arcs because they are directed paths. And so the best you can do is pack 3 pairwise arc disjoint die paths. Okay, and so that turns out to be our minimization problem. Given a digraph D with specified vertices S and T, the source and the target, find an ST dicut. So now I need to define what this is. Find an ST dicut of minimum cardinality. Right? And when we say ST dicut, we mean a cut partial plus x such that S is an x and T is an x bar. Okay? And so notice that based on our previous discussion already, ST dicut is not the same as a TS dicut. Right? In a digraph, the order matters. So when I say ST dicut, I really mean S is on the left side, T is on the right side, and you're looking at arcs going from the left to the right side. Right? Good. Whereas, of course, in a graph, G, ST cut is the same as TS cut. Okay? And so basically, what you can now do is you can write down all of the statements that we wrote previously for directed graphs. I will not even spend time on writing all of them one by one. I will just go through what we wrote and tell you what the corresponding statement for directed graphs is. Okay? So this corollary just changes very simply. If you have a directed graph with a source S and target T, if there is an ST dicut of cardinality K, then there are going to be at most K pairwise arc disjoint ST dipaths. Okay? So I'm just going to maybe make changes here. Let's see. So whatever is written in red is for directed graphs. So you change this to dst, and if you have an st-dicut, then you will have D has at most k pairwise arc-disjoint st-dipaths. Right? And the proof is very straightforward. We just did it by drawing. You can write down a formal proof yourself. Okay? Because each dipath must use at least one arc from the st-dicut. And so you cannot have more than k pairwise arc-disjoint st-dipaths. Right? And Menger's theorem basically changes in the same exact manner, the local versions, right? So we are not talking about global versions for directed graphs because we are not talking about directed graph connectivity. Okay, so we'll just focus on the local version. For any digraph, ds comma t, there exists k pairwise arc-disjoint st-dipaths. If and only if each st-dicut has cardinality k or more. Okay, and well, you can change the same, make similar changes here. Okay, good. And then you can write down the optimization point of view, which we already actually discussed. I wrote maximization and minimization problems. Good. All right. Are there any questions? Notice that we have not proved any theorems. So far, we have not proved anything non-trivial in this module. Okay? All I have done is I have given you the basic framework and terminology, and I have told you what these Menger's theorems are. There are lots of different Menger's theorems. Oh, I should probably tell you what the version is. So the version in red color, as you probably have guessed, is called the local arc version, right? So this works on directed graphs, and it's called the local arc version. Okay. Why are we specifying arc and edge? There are also vertex versions of Menger's theorem, and you might be proving some of them on your assignment, and they will all be straightforward or maybe not so straightforward applications of the edge or arc versions. Okay, good. So what's next? So now we are going to switch to flows and cuts. So far we have been talking about disjoint paths and cuts, and in some sense disjoint paths and cuts are sort of dual to each other. You know, if you want a lot of disjoint paths, you can't have a small cut. And what these theorems are telling you is that the maximum number of disjoint paths is actually equal to the minimum cardinality of a cut. Right? I'm skipping all the excess terminology, st-path, st-dipath, st-cut. You get the idea, right? So in some sense, paths and cuts are sort of what we often call in combinatorics. These are dual objects. They seem to block each other, and you have a beautiful min-max result. The maximum of one is equal to the minimum of the other. And we will be seeing many other such results in the rest of the course, including in the matchings part of the course. Okay? But rather than proving Menger's theorems, what we will now do is we will switch to a more general framework, the framework of flows and cuts. Right? So instead of disjoint paths, we will be looking at flows in a graph. And we will prove the max flow min cut theorem in the next 1 or 2 lectures. I will state it today if I can. And then everything else we have discussed so far will be a consequence of the max flow min cut theorem, right? So everything will be a corollary of the max flow min cut theorem. And we will also see an algorithm to find a max flow and a min cut, whatever these terms mean. Okay? So are there any questions so far? Can you all hear me?
Yes.
Okay. All right. So in that case, let us move on to a new page. All right. And unfortunately, we are going to need a few more definitions. We are going to basically generalize the concept of a directed graph. And we are going to go to what we call networks. So, oh, okay. So let me start by an example. The same example as before, but I will put some more information. Okay, so we have a digraph as before with a source and a target, but now we are going to have some additional information. Let me first label these vertices, V1, V2, V3, V4. And what we are going to do is, for each arc, I'm going to put a number in blue color called the capacity of that arc. Okay? So the capacity here is 1, 1, 1. Oh, I wanted to draw a few more arcs. I will do them. This is 1, 1, 4, 1, and 4. There are 2 more arcs I wanted to draw. And both of these have capacity, let's say 3. Okay? So we have a directed graph, and we have put on each edge or each arc a number, a non-negative real number, which is called the capacity of the arc. Generally, in examples, I will just put down integers, but we are going to allow, in general, for non-negative real numbers. Okay? And so that brings us to the definition of a network. Okay, so a network N, we are going to have a directed graph, D, with a source and a target, S, T. But in addition to this, we are going to have a function which is called the capacity function. Okay, so it is a directed graph. With a capacity function. C, which takes any arc of the directed graph and gives it a non-negative real number. Okay, good. All right. And what we want to do is we want to send a flow So I'm going to write informally without putting any definitions. Our aim is to, this is like think of this as a maximization problem. To send a flow from S to T. Okay, what does that mean? We will talk about it in a few minutes. Okay, so the reason we are doing this is, one, because this is a more general framework which implies all of the arc disjoint, edge disjoint stuff that we were already discussing. So we will talk about flows and cuts, and so that's one reason. It's a more general framework. And the second reason is, actually, this is one of the results in theoretical computer science, combinatorics, whatever, that has actually found tons and tons of applications. So you can think of a lot of real world problems, like lots of companies like Amazon, you take, I don't know, Flipkart, Walmart, they all need to solve a lot of flow problems because they want to send items from their warehouses to various stores across the country or across the world, right? And in order to do this in an optimal fashion, they need to solve lots of flow problems. Now, of course, they may not be exactly the kind of flow problems we are discussing. They might have some even more complicated flow problems, which might be somewhat non-linear or whatever. But the point is, in order to solve harder problems, one first needs to understand how to solve the most fundamental of problems, right? And flows were actually used heavily, even in various, unfortunately, also in many wars and stuff, to optimize the operations of various countries and armies and stuff. So all the way from industry to warfare, flows have actually been extremely useful in optimization. And of course, even in things like, if you have a vaccine, how do you distribute it to the entire country in an efficient manner? Well, this is a very relevant problem for today's age, for today's day. And again, a lot of these turn out to be actually flow problems, right? So flows have found immense number of applications. I think it is probably the problem that has found the maximum number of applications in industry, from theoretical CS and combinatorial optimization. Okay, good. All right, so let's go back to the math and see how we can formalize all of these notions. So what is an example of a flow? I want to give you an example of a flow in this particular directed graph. Okay, and I'm going to write down the flow in red color. Okay, so what we could do is we could send a flow of one on this arc and one here, let's say one here. And notice that I'm always respecting the capacity. So if an arc has a capacity of 4, I have to send a flow of less than equal to 4 on that arc. Okay, so this is going to be one of the conditions for what a flow means. Okay, I may send 0 here, I may send 1 here, I may send 2 here. And let's see, what about these two? Let's say I put 1 here and 1 here. So one thing that you notice in this flow is that for every arc, the flow is less than equal to the capacity of that arc. Okay. Another thing you observe here is that if you look at any vertex, for example, you look at this vertex which is not S and which is not T, right? Because we are sending flow from S to T. If you look at any vertex which is an intermediate vertex, you will see that the incoming flow is equal to the outgoing flow. So here the incoming flow is equal to 2 plus 0, and the outgoing flow is equal to 1 plus 1. Okay. Think of it, if you want to think of a real world problem that is easy to imagine, think of sending a bunch of trucks from, I don't know, from Adyar Gate to Velachery Gate, right? There's a lot of construction going on these days on campus. Well, most of you are not here to see it, but I can vouch that there is a lot of construction going on here. And they want to send a lot of trucks from one point to another point. But each road has a certain capacity. So you have to respect the capacity of each road segment, right? So that is an arc. And for every intersection, if there is a bunch of trucks coming to that intersection, they will also leave that intersection unless they are already at the destination, right? So the incoming flow should be equal to the outgoing flow at every intermediate vertex, okay? And this is what a flow is going to be. Is the intuitive idea clear?
Yes.
Okay, thank you. So now let's write down a formal definition, right? So we have a network and we want to define what a flow is. Okay. An ST flow, but many times I will just say a flow. In this module, we are always going to have an S and a T. No, well, not in this module, but in this particular discussion, we will always have an S and a T. So maybe I will not say ST flow every time. An ST flow in a network N, as defined above, right? So a network is like this, is a function f from the arcs of the directed graph to non-negative real numbers that satisfies the following constraints. Right? So constraints are basically conditions, right? So the first type of constraint is called a conservation constraint. So what does conservation mean? If you look at any vertex, oh, by the way, I need one notation. So the one notation I need is the intermediate vertices of a digraph in this setting are all the vertices of the digraph except the source and the target. Okay? So in this graph, the intermediate vertices are V1, V2, V3, V4. Okay? So for each vertex that is an intermediate vertex, okay, I need a little bit more notation, but it's okay. What I want is the sum of the arcs coming into V. So if you look at any arc which is going out of V, that is going to be the same as the sum of the arcs coming inside V and sum of their flows, right? So this is the, in colloquial terms, the outgoing flow is equal to, outgoing flow at a vertex V is equal to the incoming flow at the vertex V. Okay? And second is the capacity constraints. For each arc of the directed graph D, we want that the flow on that arc is at most the capacity of that arc, right? If a particular road segment can only handle 5 trucks at a time, then you should not send more than 5 trucks at a time, right? So that is all that the flow capacity constraint is saying. Okay, So to simplify, I don't want to write so much notation each time. This is a lot of notation. So let us simplify things a little bit. Okay. All right. So let's do the following. For a digraph D and function f from the arcs of the digraph to non-negative reals, if you give me any subset, if y is any subset of the arcs, we let f of y, notice that the function is defined for each arc, right? But now we are going to take a subset of the arcs, and what we will do is we will define a function on the subset of the arcs by just summing up the values on each arc, right? So we let f of y equal to, you take all the arcs in the set and you sum up their function values. Okay? To give you an example, supposing I take these two arcs, 1 and let's say 2. Can someone tell me what is the function defined on SV1? When I write an arc like xy, I mean this, okay? I will not probably always write an ordered pair, okay? So x is the tail and y is the head. So what is the function for SV1 and V1, V4? Note, remember that f here is the red colored numbers. Anyone? I've picked up two arcs. The first arc is SV1 and the second arc is V1, V4. So what is f of SV1, V1, V4?
2, right? Oh, sorry, 1. Or
1? Or is it 1 plus 1, 2?
2.
2. Okay, good. So this is just to simplify some stuff. And what we are going to need more than just a set of arcs is we are going to need cuts, okay, as you probably have already guessed. So for a subset X, sorry?
Definition is all right, but intuitively speaking, when you say those two edges, there's only one quantity flow, right? Like there's only a flow of one going. It's the same
Right.
flow to both edges.
That is true. That is true. That's right. But we are going to define it as the sum of the flows on each arc.
Okay.
Yeah, because the thing is, well, you're looking at these two arcs, but right, I mean, if you look at two arcs which are far away, let's say I pick this arc and then I pick this arc, right? Then it's not clear what the flow across these two arcs is, right? I mean, you get the point? Right.
Yes.
So yeah, maybe I should have chosen a more non-trivial example, but yeah, you're right. Okay, so we are going to define the flow on a set of arcs as just the sum of the flows on each of the arcs individually, right? And the reason is simply convenience. We are going to find this notation convenient to simplify stating things, okay? And what is going to be more useful than an arbitrary set of arcs is a set of arcs that comprises a cut of the graph, okay? So for a subset of the vertices, what we will do is we will say f plus of x is equal to f of partial plus of x. And f minus of x is going to be f of partial minus of x. Okay, let's do some examples to understand what this means. Okay, so I'm going to look at the same example. Well, it's a mess actually. Let me redraw the thing. Let me make a small example and just, okay. Okay, just some simple example like this. Maybe I'll put one more arc. Okay, and this time, notice that I just need a digraph and I just need a function, right? I don't need a whole network. So I'm just going to put down a digraph and a function in red color. Okay, 2, 1. I don't even care about the constraints, right? I mean, this is just some arbitrary function defined on a digraph's arcs. So I actually don't care about anything. Let me not put minus, I mean, let me put non-negative real numbers. Okay, some arbitrary function like that. And let me look at this set as my x, and this is my x bar. Notice that here, I don't even need an s and a t. Okay, so this is an arbitrary function in red. Okay, and so now I want to ask you, what is f plus of x? Can anyone tell me what is f plus of x?
8.
8. Exactly. Because what you do is you look at all the arcs going out of x and take the sum on those arcs. So you get 1 and 7. Okay? Right? So this is exactly this quantity. You look at all the arcs going out of x and you sum up the numbers on those arcs. That is x plus x. So that is equal to 8. Okay? And what is f minus of x? Anyone else? What is f minus of x?
3.
3. Exactly. Okay? Because there is only one arc coming from x bar into x. So you just sum up those numbers, which is equal to 3. Okay? Great. And what would we do if something is the empty set? Let me just take a look. So what if x is empty? So what if, no, not x. What if partial plus x is empty?
Zero.
Exactly. Then f plus of x would be 0. Right? Of course, that is not the example I drew, but just to give you an idea. Okay, good. So we have defined a bunch of things today. And I think we have, what is the time now? Okay, so I think we have crossed the time. So let's continue tomorrow. We know what an ST flow is. And we are going to talk, well, not tomorrow. On Monday, we will continue with this topic of flows and cuts. And very soon, maybe on Monday or already by Tuesday, we will know what the max flow min cut theorem is all about. And then we will proceed to prove the theorem. Okay? So if there are any questions, please stay back. I actually have a very important meeting to attend at 12 o'clock. So I will have to leave in the next 5 to 7 minutes. But I have office hours today. And one of the TAs also has office hours today. I think it's Shantini at 4 p.m. So please ask questions right now, or otherwise attend office hours to ask more questions. Okay? But yeah, I do have another 5-6 minutes, so please stay back and ask questions.
Sir, we have already seen the max flow min cut theorem and its proof in the previous lecture. So can we like go a bit faster with the content, if that is okay?
I see. Yeah, that's a good point. Okay. How
Maybe you
about
can tell them how.
how about
uh,
matchings? How about matchings? How many of you have already seen matchings?
You just saw one application with bipartite matchings of the Max-Flow-Menger theorem. So
Okay, but have you studied matchings extensively or just as an application of Max-Flow-Minkert theorem?
no, just as an application.
In the
Okay.
graph theory course, we learnt about Hall's theorem.
Oh, you learned about Hall's theorem in graph theory course. But did you learn about an algorithm for bipartite matching that does not go through Max-Flow-Minkert?
No.
No. So you have not studied augmenting paths in matchings.
No.
Okay, great. So what I will do is I might hold a poll to find out how many of you would like me to go over max flow min cut really quickly. And if there is a significant number of you who would like me to rush through the max flow min cut part, then I will try to hold extra lectures for those who have not seen it or those who would like to see it again. Okay. I am not making any promises right now because I'm actually going through some personal crises at the moment. So I will try my best, but I won't make any promises right now, and it will depend on the results of the poll. Okay, and I might also discuss with Meghna and other instructors to find out what all they covered in their courses. So just while you are here, Dev, what is the specific course in which you studied Max Flow Min Cut?
CS2800, design and analysis of algorithms.
And this was taught by Meghna?
Yes, yes.
Okay. What about others? Have others also seen it in the same course, or is it a different course taught by someone else?
You're on the same batch, sir.
Oh, you're all from the same batch, so it was the same course. Okay. Okay, great. So I'll have a discussion with Meghna and I will hold a poll to find out how many of you would like me to not spend too much time on Max Flow Min Cut. Okay. And if there is a significant number, then I will hold extra lectures for students who have not seen it or who would like to revisit it. Okay.
Okay.
Cool. Thanks. Thanks for bringing this up. Because yeah, I don't want to make the course boring for those of you who have already seen some of the material. Any other questions, suggestions, discussions? I have another 2 minutes, after which I'll have to leave the call.
No, thank you, sir.
Okay, have a good weekend. But yeah, I'm still here for 2 more minutes. I hope everybody has submitted assignment 1. If you haven't, then well, maybe you should write to me and discuss with me what went wrong. Because doing the assignments is really important, not just from a grades point of view, but from an actual understanding of the course point of view. We will try to get the assignments marked and returned in the next 1 week or 10 days. All right, so I'm going to stop recording and close the meeting. and have a good weekend. And please do attend the office hours if you have any questions or if you'd like to discuss anything. Bye.